SwayamPrabha. Digital India. Educated India.
When we started this course, we had made three broad classifications in acoustics. Physical acoustics, which was essentially about how sound propagates in air or in medium in general from point A to point B. Then we had also talked about electroacoustics. That was another big category, which concerns itself with transformation of sound into other forms of energy or other forms of energy into sound. And then the third big area was psychoacoustics, how the mind, the human brain interprets sound. So that was the introduction. Then we talked in detail about, or somewhat in detail about, physical acoustics. We went through this plane wave equation, one-dimensional equation in Cartesian and spherical coordinates, interference of waves, stuff related to physical acoustics. Then we moved into the area of electroacoustics. And primarily in area of electroacoustics, what we have talked so far is how is sound generated in engineered systems. In natural systems, sound gets generated. We have not talked about that. But in engineered systems, systems which human being devises and designs, how is sound generated. So we have talked about that. Today we will still talk about electroacoustics, but we'll focus more on how is sound received or recorded, because that is important to understand from an engineering standpoint for two reasons. If I have sound of quote unquote of a specific type, and we'll explain what this type means, then what kind of microphones should I use? That understanding has to be there. The second thing is which microphones are good or not so good in a particular application. We have to understand that. So today we'll primarily talk about microphones. We will not talk so much in terms of how microphones can be designed, but how we can intelligently use microphones which meet our needs. So in that context, we'll talk a little bit about the design at a little detailed level, but we will not go too deep into the detail. And then we will also try to map different types of microphones into different types of applications. Microphones essentially measure pressure, or in some cases they measure pressure gradients, differences in pressure. So in general, these are two big broad categories of microphones: pressure microphones and then pressure gradient microphones. And then there is a third category which are hybrid, which work on the principle of a combination of both of these, pressure and pressure gradient. So we'll start with pressure microphones. We'll start with pressure microphones. And within pressure microphones, there are different types or categories of microphones. There could be electrodynamic microphones, there could be condenser or capacitor microphones, there could be piezoelectric microphones, there could be carbon microphones. We will very briefly capture all of these, but let's start understanding how a pressure microphone works. So essentially what a pressure microphone is that I have a casing, and then I have a diaphragm which is attached to a suspension system. So this is my diaphragm. This wiggly line represents the suspension system, so the diaphragm can move in and out. On the back side of the microphone, now this diaphragm could be metallic, or it does not have to be metallic. It's a film. It's a thin film. On the back side, I have a perforated surface. Diaphragm and the back perforated surface there electrically, and then I seal this entire thing. Also, what I have is a small orifice here, which is in green. So I have diaphragm, which is member A. I have a perforated screen, which is member B. Everything into an enclosed cavity, and I have a small orifice. Which is here, and my pressure wave, when it hits, it gives me a pressure. It hits the diaphragm, so the diaphragm sees some pressure. Okay. The front membrane and the back membrane. So what we are talking, this is a particular type of pressure mic, what we are seeing. It's called a condenser mic. The front membrane and the back membrane are connected to a resistance which is very high in number, very high value of resistor. And then I have a battery source which provides what I call polarizing voltage. The diaphragm and the surface B, they are made up of dielectric material, so they can store charge. Electrical sense, this entire thing looks like I have a DC supply, a very high value of resistance, and then these two flat plates are like capacitors, make a capacitor. And what I measure is basically this parameter V0, which is the voltage across these two plates. Actually, more often I measure the charge, Q. So these two plates, they are separated by a distance, some nominal distance. Let's say this distance is D. So my capacitance is C equals area of the surface times permittivity constant over the distance D, right? Now when a pressure wave hits the diaphragm moves in, or if it is negative pressure, then it moves a little bit out. So what I am doing is I am sensing changes in this charge Q, and then I interpret that change in charge because my capacitance is changing, right? My Q is basically C times V0. When capacitance changes, charge is changing, and I sense that change in charge, and from that I interpret, try to extract what is the pressure which the diaphragm is seeing. So what I have drawn here is basically the electrical component of the circuit. There are also a mechanical component of the circuit. You all have now the fundamentals to develop a mechanical component of the circuit. Electrical and acoustic component merge into this thing, and you can figure out when it sees a pressure P, how does Q change, right? You can figure it out. So I'm not going to go into detail in that aspect, but this is how the pressure microphone works at a very basic level. As you are developing the acoustic component, bear in mind there's a cavity here, so it has some springiness. There's also a mass of the diaphragm. There's also a stiffness of the diaphragm. So all that has to be taken into account when you develop the entire thing, if you want to. Someone may ask, why do I have this surface be slotted? And the essential reason for that is there could be some frequencies which may excite the resonance of surface B. So then it does not behave in a very controlled way. So what the perforations do is that they act as acoustic resistors. So when you are developing the acoustic circuit, you have to include that resistive element. And what that resistance does is it damps out the vibrations. So this is capacitor mic. This is a capacitor microphone. If my pressure goes up, my charge increases linearly, and what we see from this very simple analysis is that the change in charge does not depend on frequency. There is nothing which is embedded in the frequency part of frequency term is not embedded in this relation. So Q changes regardless if a pressure wave is hitting at 1000 hertz or a pressure wave is hitting at 50 hertz or a pressure wave is hitting at 20,000 hertz. If the value of that pressure is same, Q will change by the same amount. So the response, there's only one caveat, that the size of this device has to be significantly smaller than the wavelength of the frequency, wavelength of the perturbation. If I plot PD, PD is basically the pressure difference outside and pressure difference inside. Inside it's atmospheric pressure, because I have this small orifice, because when you move from microphone from location A to location B, you can take it in aircraft, pressure can change. So I have that small orifice to make sure that the ambient pressure is same as whatever is the ambient pressure outside. That is the purpose. So PD is basically P outside minus P inside, right? Which is basically P. So if I plot PD versus log of omega, as long as my lambda, my size of the object, which I can represent by this dimension A, is significantly small than lambda over 2 pi, then my response curve is a flat curve. So a device of this type gives me a fairly straight response curve over, I can make this range as much as I want by just basically shrinking the size of the microphone to whatever value I like. So this gives a very linear response over an extended frequency. But because I have to have this charging battery in it, this is an expensive device. This is, I have to provide a polarization voltage, and to make that happen, that requires a lot of money. So this makes things very expensive. Also, the tolerances required in construction of this kind of equipment are very tight. This particular type of a pressure microphone is expensive to make. Very expensive. So this is one type of a pressure microphone, which is called a capacitor microphone.
You said that the charge does not depend on the frequency. But the way it changes does depend on the frequency.
What do you mean?
Because charge is dependent on the capacitance, and the capacitance is dependent on the effective distance, which will change with the vibrations.
It will change with the vibration. In what sense? If I am putting a pressure, regardless of whatever frequency it is, let's say it has a value of 5 newtons per meter square, then my member will just move in accordingly by the same amount.
It's a pressure wave, so accordingly it will vibrate, and because of that the effective distance between the two membranes will change with a frequency same as that the pressure wave hitting the entire thing.
And rate of change of charge will depend on frequency.
Rate of change of charge will depend on frequency, but not the charge.
Yeah, I'm just asking.
Yeah.
That.
But that's why we are measuring charge. So the rate. So yeah, we are not measuring current. We are measuring the charge, which is an integrated quantity. So that will not depend on frequency. That's why.
And sir, the perforations that you talk about, the same thing can happen with the diaphragm also.
So they engineer diaphragm in such a way. You cannot make the diaphragm also perforated.
That is.
So you have to engineer diaphragm in such a way that now as you keep on shrinking the size of the diaphragm to make things smaller to meet the frequency, it also automatically starts becoming more and more stiff. But yes, engineering diaphragms, if you want to measure up to 20,000 hertz, the full band, audio band, then engineering it is not easy. It's a very difficult thing to do.
Because your stiffness will increase, and then we have to.
But in theory, you can make things as small as possible, and that will give you a linear response. Inherently, in the mechanics of the system, there is nothing which says that the response will be not straight as frequency changes. That's all. What else? So the second type of, so this is in a very broad sense, this is a pressure microphone, because what we are measuring is changes in pressure. The second big category is pressure gradient microphones. These microphones are also called by some people as velocity microphones, and we'll see that a little later why they are called velocity microphones. In general, the way these mics work is that you have again a tube so you have a diaphragm and you have this kind of a tube which is not long. Now my pressure wave is coming from this side. Let's say this is called P1. This pressure and this has fairly wide slots. So unlike a small orifice for equalization of pressure, what you have here is a fairly wide gap which can enter into this tube or a cavity. So the pressure can, sound also travels like this. And let's say this length is delta L. The length, so let's say this pressure on the inside, which when it hits the diaphragm is P2. Sound travels delta L distance more for pressure P2 because it has to go inside and hit it. So there's a change in pressure associated with some delta L. So essentially what we are measuring here is the pressure gradient. So PD, which is the difference in pressure, is mathematically we can say gradient of P times delta L. It's a dot product of these two vectors, where P1 is pressure outside the tube near the diaphragm, P2 is pressure inside the tube near the diaphragm, delta L is the distance, difference in distance traveled by the two waves, and it's a dot product because when you have a gradient, it's a vector and it has some directionality associated with it. So this delta L has to be aligned with that gradient. So this is essentially del P over del X. For instance, if I am only thinking about X direction times delta L, which is a scalar, times cosine of theta.
So this delta L is the entire distance from outside to the...
Yes, but we have to take its dot product. So in this case, if the direction of P1 is same as this length of this length, then basically literally the delta L will be this length plus this length, right? Twice that long. So now what we will do is, let's look at a scenario when this whole device is at an angle from P1, and let's see what it does to us. In this case, which is case A, theta is 0. But what we will look at it is another scenario. So case B, theta is not equal to 0. I'll have to make a rather long big drawing just so that things are visible. I have to make a gap. That's my P1. My delta L is associated with this path. This angle is theta. My pressure difference is minus gradient of P times delta L times cosine of theta. Why did I have negative gradient of P? Because, I mean, if I look at it physically, if P2 is larger than, listen, I have to define a coordinate system. So this is my coordinate. So going forward is positive x. If P2 is larger than P1, then the displacement in the membrane will be negative x direction, right? So for positive gradient P, I have negative x. So that's why I have a negative delta P. So PD is minus delta P times delta L times cosine of theta. Again, the standard things that the size, this dimension A has to be small compared to the wavelengths we are going to measure. All that has to be clear. For theta equals 0, PD is maximum. For theta equals 90 degrees, PD is minimum, which is 0. So in this kind of a contraption, I am measuring the movement of the membrane, which is basically a consequence of the difference in pressures attributed to a delta L. So that's why it's called a pressure gradient microphone. P, we know x omega is P plus E minus j omega x over C. I am assuming in this particular relation that I have a forward traveling planar wave. There's nothing, no reflection happening. So there's no P negative term. So gradient of P is minus P plus omega j over C E minus j omega x over C. So my PD is minus, I'm using this relation, minus gradient of P. So it gives me, the minus terms become a positive, P plus omega j over C E minus j omega x over C times delta L times cosine of theta. So I'll just rewrite this relation. PD equals P plus omega j over C E minus j omega x over C times cosine of theta times delta L. So if there's no reflection, then basically P1 is same as P plus, right? If I am trying to plot PD and I do a Bode plot, so I have a log omega, here I am plotting decibels for PD. How will the curve look like? For a given value of x, the question is, see at this point x is defined, wherever my wave is hitting the microphone, x is defined, so x is not changing. Theta is not changing. For a given value of x and theta, if I change the frequency, how does PD change? What will be the curve look like? It will be a flat line, or positive slope, negative slope, what will it be? Why will it be?
Positive slope.
It will be positive slope.
But
Omega. There is nothing positive, negative here. Right?
it won't pass through origin.
Will be something like this, right?
Negative intersection.
Yeah, I mean, and this will be some, I think it will be 20 dB particularly. Yeah, 20 dB. So that's my transfer function. So clearly this is not a, so for different frequencies, if I am measuring PD, for the same amount of PD, same magnitude of PD, if I measure it at 100 Hertz, the signal measured in terms of voltage when the membrane moves will be 1. If I measure it at 1000 Hertz, which is a decade apart, the signal measured will be 20 decibels less, right, because of this relation. So I don't like this. And that is coming essentially because of this omega j over C term. How do I get rid of this term? What I can do is I can integrate this guy. So omega j over C goes away. So I can multiply this by 1 over j omega. So the omega term goes away. Or in electrical terms they use this word called integrator. So my input is PD, and whatever voltage I am getting is after integrating it, so I get rid of this. So once I integrate it, my response curve becomes how will be the response curve look like? That omega term goes away. So what will happen? It will become a flat straight line. right? Shalin, did you get it?
Sir, but there is this E minus j omega x by c.
X is fixed. All what I am plotting is the transfer function of PD with, I am plotting a transfer function of PD with respect to the incident wave. So this E minus jx term gets eliminated. So I get a flat straight line.
This will be P, not PD.
You can call it. I am being a little sloppy, yes. So this is voltage. So I get a flat straight line. So this is how pressure gradient microphones. They are also called pressure gradient. They are also called velocity microphones because we know that from Newton's law. I think this is the relation, right? So they are also measuring basically velocity, especially after you have done the integration, then the velocity. So that's why they are called velocity microphones. But in the truest sense, they measure pressure gradient. This is the response for a plane wave. And once I integrate it, this is the response for a plane wave of a pressure gradient mic. But in real application, suppose I am speaking and it goes to you, it may not be a plane wave. You don't know whether it's a plane wave or it's a spherical wave. So let's also see how it responds, this kind of a contraption, how it works for a spherical wave. So for a spherical wave, the wavefront forward going without any reflections wavefront is E plus over R, E minus j omega R over C. And let's say my wavefront is such, these are spherical waves in this direction, and the orientation of the diaphragm is like this. This is my diaphragm. So my gradient of P is what? P plus E minus j omega R over C times minus 1 over R square minus j omega over CR, which I can simplify as minus P R omega times 1 over R plus j omega over C. So my PD, which is the difference in pressure, is minus gradient of P times delta L, is a dot product, which is P R omega times 1 over R plus j omega over C cosine of theta delta L. So I'll just rewrite this because I'm going to do a board plot here. Is P R omega cosine theta 1 over R plus j omega over C delta L. If I plot in decibels, because of this particular term, how will my board plot look like? This is log omega. This is decibel for PD. A board plot has a low frequency asymptote and a high frequency asymptote. What is the low frequency asymptote going to look like?
Flat line.
It will be flat line. And the high frequency asymptote?
Increasing 20 dB.
It will have a positive slope of 20 dB per decade. And the actual curve will look something like the crossover point will be such that this is log omega naught, where omega naught is equal to R. C over omega naught equals to the reference wherever I am placing the microphone and how far it is from the spherical source. That here I have still not integrated. Now either in a hardware, either you integrate it or you don't integrate it. So in case of plane waves, I had decided to integrate it because it gives me a flat response. So let's see what it does in this case. So once I integrate it, basically my actual response curves looks like this. Basically the way you get it is you divide this whole bracketed term by omega, j omega. So this is again my decibels log omega. This breakpoint, which is going to be somewhere here, is going to correspond to omega naught. Above a certain point, it starts becoming flat. I mean, this is going to be an asymptote, so I should be more careful. Something like that. It becomes fairly flat. But at low frequencies, you see a spike. The other thing we have not talked about is that there is a cosine theta term in both the spherical and as well as the plane wave expressions. What that means is that if my microphone is placed in the direction of the incident wave, it will see maximum amplitude. If it is placed at 90 degrees, it will see zero value. So I draw a polar plot. And on a linear scale, the curve looks like this. These are supposed to be equal circles. This is a bad drawing, but these are supposed to be equal circles. So this is 0 degrees. The radius represents the magnitude. I don't want to confuse with this length represents the magnitude. So at 0 degrees, the microphone will be very sensitive to incident pressure waves. At 90 degrees, it will not record anything. And at minus at 180 degrees, it will again start recording at maximum level. So the response here is bidirectional. That is the first thing. Other thing is that in most of the cases, unless you are really, really far away from a radiating, single source, in most of the, unless you are really very far from, point sources, suppose I am speaking, unless you are really far away from me, this point source acts as a spherical source. We have talked about it earlier. So in most of the cases, a microphone measures sounds emanating from point sources which act as radially propagating sources. And what that means is that if I place this microphone very close to the source, what will be the measurement? It will faithfully record high frequency data because the response curve is flat in this zone. But it will record low frequency information at a higher decibel level. Now when I play the same soundtrack, in reality, suppose I am speaking, my low frequency sound or information gets recorded at a higher decibel level, high frequency gets recorded at quote unquote normal level. When I play the same soundtrack again, I will sound like a person who has more bass. This is a trick a lot of singers use, that if they want to have a lot of their heavy voice, they use this trick. They use these kind of microphones and place microphone very close to their mouth. You may have seen it like that. It's really a bass enhancing technique. Also, a lot of discussions when you hear on radio, you will feel that the person who is speaking, he has a very heavy voice. It's because of this artifact of measure. So this is the polar plot in absolute terms. And if I plot the same thing in decibel terms, the polar plot looks a little steeper. It looks like a butterfly. Something like this. because the shape of these pictures is like a figure of 8, these microphones are also called figure 8 microphones. There is some general parlance. So we have talked about microphones which measure pressure, microphones which measure pressure gradients. Now there is a third category which rely on both. So these are called, some guys call it pressure gradient microphones type 2, but that's not a very popular term, but it's pressure and pressure gradient microphones. So the construction looks something like this. So again, I have a diaphragm. So I have a suspension system, suspension stiffness here in these two wiggly things. There's a fairly rigid diaphragm, and then there's a cavity of volume V0, which is filled with regular air. And on the other side, I have a perforated screen, which offers an acoustic resistance Ra. My pressure wave hits here with the pressure P1, and the same pressure wave hits on the other side at the level P2, and that length is delta L. So I can construct a simple 4-point network for this, for just the electrical acoustic portion of this thing. So this is called ZAD. I'll explain what these terms mean. This is CA, this is RA, pressure. So ZAD is the overall impedance offered by the diaphragm. CA is associated with the compliance of this cavity of volume V0. RA we have already defined, it's acoustic resistance. P1 is pressure outside the diaphragm. P2 is pressure just outside the screen. And this is, what kind of model is this? Is it impedance model or mobility model? Because my pressure is the across variable. So let's say my volume velocity which the diaphragm is seeing is VVD, and volume velocity which the screen is seeing is VV0. Two relations here, VVD. So I am basically considering this loop, loop 1, and then there is another loop, loop 2. Okay, so my P1 is VVD times ZAD plus VVD times 1 over CA minus VVO times CA, right? So I will write that relation, VVD times ZAD plus 1 over SCA minus VV0 times 1 over SCA equals P1. S is my complex j omega. And similarly for the second loop, my relation is VV0, VVD times 1 over SCA plus VV0 acoustic resistance plus 1 over SCA equals minus P2. So let's say this is my relation 1. So if I know P1 and P2, then I can figure out VVD and VV0. I know everything else in these two relations. So what I will do is in next equation, set of equations, I will try to compute what is P1 and P2. So P1 is my incident wave P0 E minus j omega x over C. I'm assuming again flat one-dimensional wave without any reflections. And P2 equals P1 plus del over del x P naught E minus j omega x over C times del L cosine theta. So this becomes P1 1 minus j omega over C del L cosine theta. So now I know P1 and I know P2. I can plug these in 1. This is equation 2. So if I do, so I can, from 2 I can figure out what is VD and VV0. And I also know that PD equals P2 minus P1, pressure difference between the two sides of the system. And so this is there. So if I do mathematics with all these three equations, at the end of the day, I mean this is just regular math, I can find the ratio PD over E1 is, this is a long term ZAD times RA plus del L cosine theta over velocity of sound times acoustic compliance, the entire thing divided by ZAD times RA minus J RA plus ZAD divided by omega CA. So you can play with these three relations to get PD over P1 and you end up getting this thing. Now just to make things look a little simple, I define a quantity B such that B is delta L over RA times C times CA. So my PD over P1 becomes ZAD times RA 1 plus B cosine theta alpha times 1 plus B cosine theta, where alpha is this entire term besides 1 plus B cos theta. So in case of a pressure differential mic, we had just cosine theta in the term. Here we have 1 plus some constant times cosine theta. So pressure differential mic was bidirectional just because of cosine theta terms. Here I have the flexibility to play with B. B is basically delta L, RA. I cannot change C, velocity of sound, but I can change all other parameters, delta L, RA and CA. And depending on how I change it, I can change the directional pattern of this pressure and pressure, this combination mic in whatever way I want it to be within the realm of feasibility. Let's assume that, let's say that B is 1 can assume. We can construct a mic with specific parameters such that B comes to 1. So in that case, my polar pattern looks something like this. Someday I have to take a class in drawing. Yeah. This is called a cardioid shape. So you get different form factors for this cardioid shape based on how you play with B. Essentially what this shows is that if I have a mic pointing towards you, it will sense your sound, and if I am opposite you, behind the mic, it will not sense my sound. So this is also a directional mic, but I can change the shape of this by playing with B in different, I mean, to a certain extent. So we have seen a pressure mic, how it operates and what kind of features it has. Then we have seen a pressure gradient mic, and then a combination of pressure and pressure gradient mic. I forgot to mention one thing, that why is this called a combination mic or a pressure plus pressure gradient mic? And the reason for that is that in the process, when we are developing this entire relation, somewhere in the middle, we will come across a term, where PD will be something, a longish expression, Z AD P1 RA plus P1 minus P2 over J omega CA. Basically, the way you get this is, if you solve for V and V naught and then find PD from there, you get this relation. And what this shows is that pressure differential is a function of, depends on P1 minus P2, and it also depends on P1. That's why it's combination. So from a mathematical standpoint, this is what I wanted to cover today. So now in next 25 minutes, what we will do is, we'll just in a subjective sense, we will go over, we now understand at a basic level how different types of mics work, how based on their designs they can be directional in specific directions. So based on that, what we will do is, we'll discuss different types of microphones and how they are relevant for specific application. We have pressure mics, and there are 3-4 broad categories. One is electrodynamic mic. An electrodynamic, so in pressure mic there are several categories. First one is electrodynamic. Think about this. If you have a transducer, a speaker, which we discussed in last several lectures, instead of exciting it with a voltage, if I don't excite it with a voltage, but I just throw sound energy at it, so pressure waves hit the diaphragm, what will happen? The diaphragm is going to move, and that will induce current in the voice coil, right? That is how an electrodynamic mic works. It's basically an inverted acoustic transducer. Some people also call it moving coil microphone, because the coil is moving. An electrodynamic mic can have one membrane, but a membrane, if it is this large, it will have its own modes, which can be below a certain threshold. So some mics, some more fancy mics of electrodynamic category, they have several membranes to get an extended frequency response for the system. So this itself can be single membrane, and then multi membrane. This is a fairly commonly used mic. Because it is a pressure mic, is it omnidirectional or is it bidirectional or in one direction. It's an omnidirectional. Senses pressure, doesn't matter how the mic is oriented, right? It will just sense the pressure at that point. It's not sensing pressure differential.
Sir, but it has a cos theta term.
It is?
It has a cos theta term.
At certain theta it will not sense, but otherwise it will sense.
In theoretical, from purely theoretical standpoint, it should not have sensitivity to direction. You have a microphone like this, and all it is sensing is pressure acting on this membrane. So if pressure acts in all directions at a point, right? Pressure acts on all directions. Pressure gradients are direction specific. If I make it like this, pressure is still acting inside. The electrodynamic mics are fairly omnidirectional. So if you place an omnidirectional mic and there's a crowd, doesn't matter where the person is sitting. If you have a round table discussion, you put a microphone in center, people all around it, their sounds would be picked up by the microphone. Also, by nature of their construction, these microphones are resistant to moisture, which is an important thing. So, and they are fairly inexpensive to make. So they are very widely used. The second one is capacitor mic. Capacitor or condenser. We discussed this earlier today, right? Where we are actually measuring the charge on the capacitor. Now, within this, there are two types: polarizing and non-polarizing, or others also call it electret. So, in polarizing, we have seen in the earlier part of today's lecture, you have to put an external battery to provide an initial charge, polarizing charge across the two capacitive plates. That makes things very expensive. The polarizing type of mics are very accurate, and also they have a very flat frequency response, because when we did a very basic analysis, we saw that the relationship between pressure and omega is of a flat line, right? By the way, electrodynamics mics may not have a flat frequency response as flat as capacitor/condenser mics, because as we saw, the response of a regular speaker, it's not flat, it has different bands. So electrodynamic mics behave in terms of frequency response similar to speakers. We were on polarizing mics. Now electret mics, they do not have a charge provided by an external battery source. Rather, what they have is that the two parallel plates are essentially made of dielectric materials, and they have charge deposited on them to begin with. How do they do it? What they do is that when the thing is being made, you take a dielectric material and then it is heated up. When things are in heated state above a certain threshold, the polar molecules in that dielectric materials, they can move back and forth. So they heat it. The polar molecules have a propensity or freedom to move and orient themselves, and in such a state they apply the manufacturing process such that an external electrostatic field is applied. So you have a positive and negative, and electrostatic field is passing through. Between the field you place this film, which is made of dielectric material in a heated state. So these polar molecules orient themselves accordingly. Okay. In that state, then the thing is cooled. So then the molecules don't revert back to whatever other orientation. So then you have a permanent charge built up on both the plates. You have a positive charge and negative charge built up on both the plates. So that makes things less expensive. So because of this, electric mics probably today are the most popular microphones in the world. So they're really cheap, and this can be mass produced, because basically a lot of these films are like pieces of plastic, cheap plastic, and they deposit charge on them through this process. A drawback of these is that over a period of time, this charge starts dissipating because of heat, moisture, and all that. But again, these also from a theoretical standpoint, they have a fairly flat frequency response. If you make them small enough, you can enhance the frequency spectrum of the microphone to as much as you want. They are very reliable. They are still not as good as the polarizing type of microphones, and it's not that you cannot make these microphones as good as the polarizing microphones, but when you are doing large scale production processes, you have to maintain bigger tolerances, because production processes have wide tolerance. They want to have as wide tolerance as possible. So once you make things in very large volumes, the quality or the fidelity of an instrument goes down. If you make one piece at a time and pay a lot of attention to every single piece, you will do a better job. So because of that reason, because they are mass produced, in general they don't have as high a quality as the polarizing microphones. But again, they are omnidirectional, and these guys are used in a lot of applications. There's a microphone here, sitting here in this tablet. In your cell phones, you have an electric, most likely you have an electric mic. Computers, almost all places where you need very small microphones, these things are sitting there. Okay, so that is condenser. The third one is piezoelectric. Again, this is also a pressure mic, but what it does is it senses pressure due to when pressure gets exerted, the crystal generates a voltage, that voltage is sensed. So that is the third category. The fourth one is carbon resistance. These are kind of obsolete now, but earlier, especially in a lot of analog telephones, you would have these mics, and the way they operate is there's a small button in the device which is packed with carbon granules. As the pressure wave hits a surface of this button, it presses. So the resistance of the carbon granule changes accordingly in some predefined way. That resistance change is sensed by the electronics, and that gets recorded or converted into sound. So it was used a lot in old type of telephones, especially those black telephones. You may still see some of them lying around, and also in recording industry they were used. So these are four major types of pressure microphones: electrodynamic, capacitor, piezoelectric, and carbon. Let's look at pressure gradient mics. Okay, these are directional. We have seen through the mathematics. Specifically, they are bidirectional. So at 0 degrees and 180 degrees, they have maximum response. At 90 degrees, the response is virtually zero. Given that if you have a public address system and the requirement is that the microphone should be able to pick up the voice of, let's say, the speaker and the voice of the crowd which is on front side, people tend to use these type of microphones. So it depends on the nature of the requirement. While these microphones are used, you have to pay more attention to the frequency spectrum. You have to pay attention even in pressure mics. I mean, what is the frequency band? But here we saw that the frequency spectrum is boomy at low frequencies and flat at high frequencies. So one has to be careful as I mentioned earlier, a lot of singers also use it for the special feature that these microphones tend to produce more boomy sound at low frequency. And then the third category we talked about is pressure and gradient mics combo. So again, here you have the advantage of directionality, and these mics as well as pressure gradient mics, again, both these are very frequently used in broadcasting systems because of the directionality feature. In auditoriums, suppose you have play happening on the stage, or you have a bunch of singers, you don't want the noise or the sound of the audience to get picked up by the microphone, right? So you'll use a combination of some of these types.